let's turn our attention to this idea that there are really strong limitations, first of all, in the amount of information that we can process and hold in working memory. So let's start with a relatively simple test. I'll give you 5 words, repeat them, see if you can remember them, and repeat them back in just a second. So here are the 5 words: person, woman, man, camera, television. Okay, now I cover them up. We give ourselves a couple of seconds here. Now, see if you can repeat those same words in the same order. Did you get person, woman, man, camera, television? If you did, then you passed this basic test. And you probably didn't find it too difficult. This is at the lower end of the normal range of capacity for working memory for relatively short words like this. And so probably most of you did fine. What about if I give you the following list, though? Yellow, 2, dog, high, wind, slight, tickle, hello, mobile, and robe. Let's repeat that one. Yellow, 2, dog, high, wind, slight, tickle, hello, mobile, robe. Now I obscure them. I'm going to give ourselves a few seconds. All right. And now see if you can repeat those words in the same order that they appeared in the list. Probably going, I'll see yellow, 2, dog, high, wind, slight, tickle, hello, mobile, robe. You probably found this difficult, if you could even do it. Probably you couldn't do it because this list has 10 items. They're all small words, so that helps. It has yellow, 2, dog, 3, 4, 5, 6, 7, 8, 9, 10. And 10 items is actually just outside the normal capacity range of our working memory for these relatively short words unaided by various mnemonic tricks. So you can see, right, this really isn't a bunch of information. This isn't very complicated, and yet it really does start to exceed the limitations of our capacity that is cashed out in terms of the amount of information that we can hold in working memory. Now, let's look at limitations in the complexity of information that we can hold. And here we're going to go to a video from Dan Simons. I'll play the video, then I'll stop in the middle, then I'll play the rest of the video, and then we'll talk about it.
Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes.
Okay, so how'd you do? In general, people tend to do pretty well. They tend to get somewhere close to the 15 if they don't actually get 15. But now let's cut back to the video and see what else is going on.
But did you see the gorilla?
So this has gotten to be a pretty famous or infamous video. Many of you might have already known what was going to happen. But if you were a novice, if you've never seen this before, and you didn't notice the gorilla, don't feel bad. In the experiments, Simon reports that only about 50% of the subjects who are shown the video actually see the gorilla whilst trying to count the passes of the basketball between players wearing white. So half of the people who view this probably don't see the gorilla, even though the gorilla walks through slowly, pounds its chest, the people in white are actually rotating around it, and so on. Now, why is that? How can it be that people don't see that gorilla walk through that scene? And the answer has to do with a limitation in the amount and complexity of information that can be processed and given to our visual working memory, specifically visual attention. So in order to count that basketball, we have to focus our visual attention. We have to foveate, move the most sensitive part of our eye to watch that ball as it goes around from person to person around the screen. And our ability to get things to enter into visual working memory is key to our ability to foveate on them. So when we foveate on things, we're capable of pulling that information from our visual system into our visual working memory. If we aren't foveating on something, if our attention is on the basketball and not on the gorilla, then our brains don't actually pull that information out of the visual scene and put it into our visual working memory. In effect, we just don't see it because our brain is trying to put only the information that it thinks is important into our visual working memory. Why? Because it's very small. The visual scene is very complex, and as a result, we can only get a small amount of that visual scene and only just a few properties of the things that we do see. And as a result, when something is not being focused on, when we're not training our visual attention on it, we have a good chance of not seeing it. Let's look at yet another example of this. This time we're going to focus on not on selective attention, but on change blindness. So what happened in this video? Well, change blindness is different from blindness due to selective attention. In selective attention, you're being told to guide your visual attention to some point, and because you're being directed to do that, a change that occurs somewhere else or in some other aspect isn't as easily detectable. With change blindness, you're not given any instructions about where to look or when to look or how to train your attention. The change that occurs in the visual scene is so gradual that there's a good chance your brain won't notice it. And because your brain doesn't notice it, doesn't foveate on it, doesn't turn visual attention on it, it doesn't get into visual working memory, and it's not registered as a change. In other words, there's something that goes on in the real world that your brain just doesn't detect and hence presents the world as it was absent that change. Okay, let's do one more example of change blindness then. Okay, so I'm guessing a much larger number of you actually saw that change. You saw that iceberg in the front of the picture there slowly disappear. But now I want to ask you, what were you doing during that period of time? What I suspect you were doing was rapidly scanning all over the visual scene until you identified the thing that was changing and then focusing on that so that you were aware of the change that was occurring. Now, that's an adaptive strategy. It's a strategy that you can use to not fall victim to change blindness. But notice that there are two problems with using that strategy. The first problem is that it's incredibly resource intensive. So you couldn't do this while walking around the quad or driving in your car, right? And in addition to that, because it's so resource intensive, you're only going to want to employ it when you're aware of circumstances in which you have a potential change blindness situation. And chances are you're not going to be aware of those, or if you are coming across a situation like that, it may not register in your working memory so that you can think, oh, I need to scan all over like I did that time in Wallace's class. And we'll find this as a pattern over and over and over again. There are things that we can do to adapt, to change, to modify, to make inferences and decisions in different ways. They can improve our performance, but in order to do them, we have to know them. We have to have the working memory capacity to utilize them. We have to have the working memory capacity to be aware that this situation is a potential situation where we need to employ that problem. And what we'll find over and over again is that's hard to get those three features in line when we need them consistently. And that's why it's so hard to modify our inference strategies and abilities.